Unsupervised learning, clustering and dimensionality reduction. Discover how to extract meaningful insights from unlabeled, high-dimensional data using powerful unsupervised learning techniques. The unsupervised learning landscape. Data simplification. Reduce complexity while preserving information. Feature learning. Extract meaningful representations automatically. Pattern discovery. Find hidden structures without labels. Unsupervised learning unlocks valuable insights when labeled data isn't available. Clustering, uncovering natural groups. K-means. Partitions data into K-distinct, non-overlapping clusters based on centroids. Fast and scalable. Works best with spherical clusters. DBSCAN. Identifies clusters as dense regions separated by sparse areas. Finds arbitrary shapes. Handles noise effectively. Hierarchical. Creates nested clusters organized as a tree structure. Provides cluster relationships. No need to specify cluster count. Dimensionality reduction fundamentals. Identify core information. Extract the most important features from complex datasets. Remove redundancy. Eliminate correlated features that don't add value. Project to lower dimensions. Transform data while preserving relationships between points. Visualize complex data. Make high-dimensional data interpretable for humans. Linear dimensionality reduction techniques. Principal component analysis. Projects data onto orthogonal axes that maximize variance. Identifies directions of highest variation. Produces uncorrelated features. Fast computation through eigen decomposition. Singular value decomposition. Factorizes data matrix into 3-component matrices. More numerically stable than PCA. Works with sparse matrices. Powers many recommendation systems. Linear discriminate analysis. Maximizes separation between known classes. Supervised technique that uses labels. Optimizes for class separability. Useful for classification preprocessing. Nonlinear dimensionality reduction. T-distributed stochastic neighbor embedding. Preserves local neighborhoods. Excels at visualization. Computationally intensive for large datasets. Uniform manifold approximation and projection. Faster than TSNE. Preserves both local and global structure. Scales better to large datasets. Autoencoders. Neural networks that learn compressed representations. Can capture complex nonlinear relationships. Require significant training data. Evaluating unsupervised learning results. Define objectives. Clarify what good results mean for your specific application. Select metrics. Choose appropriate evaluation criteria for your algorithm. Run experiments. Test multiple parameter configurations systematically. Interpret results. Analyze both quantitative metrics and qualitative patterns. Real-world applications. Image processing. Compress and classify images efficiently. Customer segmentation. Group similar customers for targeted marketing. Recommendation systems. Discover patterns in user preferences. Anomaly detection. Identify unusual patterns and outliers. Implementation best practices. 80% data preparation. Time spent on pre-processing improves results dramatically. Between 10 to 20 feature selection. Optimal number of features for most applications. 3 to 5 times performance gain. Typical speedup after proper dimensionality reduction. Thoughtful implementation leads to more efficient models and better insights. Key takeaways and next steps. Master the fundamentals. Understand key algorithms and their mathematical foundations. Practice with real datasets. Apply techniques to increasingly complex problems. Combine techniques. Use dimensionality reduction before clustering for better results. Stay current. Follow research on emerging algorithms and improvements. For a more detailed understanding, check out Unlocking Patterns, a deep dive into unsupervised clustering techniques and mastering PCA and SVD for dimensionality reduction by LearnSite.